Oxidizing acid. So, in fact, when we dissolve platinum, nitric acid acts as the oxidizer. Here, this is platinum's a reducer, so we end up forming platinum-4. The hydrochloric acid is just there to provide chloride ions. These chloride ions, this is a Lewis acid-base reaction here, react to form this strange-looking anion. This strange-looking anion is called hexachloroplatinate. Which you don't cover these until Chem 1B. So those are more advanced topics. All right, so basically what have we done, what do you need to know? One, you need to do metathesis. In order to do metathesis, you need to know what the three driving forces are. What are the three driving forces? Yeah, okay. Gas formation, do you know what the gas formers are? Yeah, okay, you should know the gas formers. For acid base, you need to know how to use the chart. The gas formers, what were they? H2CO3 decomposes into H2O and CO2. This is the main one that you need to know. There are some others, like, for example, if you have H plus and cyanide, that's a bad combination. That's a bad combination because these two ions, if you take H plus aqueous and cyanide aqueous, will form hydrogen cyanide gas. Hydrogen cyanide gas is very toxic. In fact, this is California used to have the gas chamber. Did you hear about the gas chamber? Where they had the gas chamber at San Quentin prison where they capital punishment. But they did San Quentin. San Quentin has a gas chamber in which they take sodium cyanide or potassium cyanide, I forgot, and mix it with acid to form hydrogen cyanide, and that's what they used for killing prisoners there.
They still do that.
What's that?
They still do that?
No, they don't do that anymore. But that was done in the old days. You don't want to mix any cyanides containing salt with acid, otherwise you could end up gassing yourself, right? What are the others? I only emphasize the two, but the others are on the PowerPoint. The others weren't that important. These are the ones I listed on the PowerPoint. This is the most important, number 1. Number 4 and 5 are important because you could end up gassing yourself. H2S, somebody did this in Ventura not too long ago, but this has a rotten egg odor. These ones aren't as common. Okay, so those are the gas formers. What else?
Would ammonia and bleach be one of those?
Ammonia and what? Yeah, ammonia. You got to watch out for ammonia and bleach. Ammonia and bleach can form other toxic gases. Oxides of nitrogen. Oxides of nitrogen are toxic. Most of them are. What oxide are you going to form? Well, it depends because nitrogen has variable charge. The charge on nitrogen varies from what to what? Nitrogen varies from +5 to -3. Therefore, I didn't specify what specific oxide of nitrogen, but if you mix bleach and ammonia, that's a bad combination because this is it. Ammonia do we call that electron rich, electron poor, or
neutral?
Well, in terms of redox, the way we look at it is by the charges. Hydrogen has a charge of, nitrogen has a charge of, we call it electron rich. Ammonia can burn. Ammonia can burn very nicely, but you don't need to burn it in oxygen. You could use any other oxidizer you want. If we burn ammonia, what are we going to form? We're going to form NOx. Now, which NOx are we going to form? Do you remember what NOx were? We had nitric oxide, dinitrogen monoxide, nitrous oxide. We had a whole bunch. Nitrogen dioxide. Do you remember that? A while back ago? And so why? Because nitrogen is variable charge. The charge ranges all the way from -3 to +5. And so which one we form, I don't know. It depends on the conditions. if you mix this with bleach, which is sodium hypochlorite, what do you know about bleach? Well, we know it consists of sodium ions and hypochlorite ions. What are the chemical properties of sodium? Very little, you know. Sodiums are very stable, quite unreactive. They don't participate in metathesis, they don't participate in acid base, and they don't really participate in redox. If they participate in redox, what would sodium ion be? It'd be an oxidizer. And how good of an oxidizer is it? It's one of the worst oxidizers on the chart. That's because you want to read the chart once in a while and get an idea of where these things are positioned. Hypochlorite, on the other hand, is electron rich or electron poor? It's electron. Why is it electron poor? It's got a negative charge. Shouldn't it be electron rich? It's got an extra electron. And I said it's not due to the charge. You don't look at the charge. What you look at are the charges. What are the charges? O is -2. Cl is +1. Is chlorine happy +1?
No.
No. Chlorine's unhappy. And so what we have here is we have a reducer and we have an oxidizer. What are you going to form? Well, it depends on the conditions, but I expect we're going to form oxides of nitrogen. Oxides of nitrogen are toxic. Don't mix bleach with ammonia, otherwise you're generating toxic gases. Okay? That's a redox reaction. This is metathesis. This is different.
Why is chlorine +1? Is it because of the
Why is
range?
chlorine +1? Because -2 + 1 has to give us the net charge.
Oh.
But is it still minus?
Normally, but Cl, what's the charge vary on Cl? Remember perchlorate? What was the charge on chlorine and perchlorate? +7. Is chlorine happy in +7?
No.
Terribly unhappy. So unhappy you can get a tremendous. Do you guys remember the what was the name of that plant in Nevada?
The one that was
Pepcon?
Yeah.
Does that ring a bell? Pepcon?
Yeah, the explosion.
Yeah, that was perchlorate. Chlorine in the +7 is very, very unhappy. In fact, these numbers are very important for redox. And so let me talk about these numbers here for redox first. So where do the charges come from? Those charges come from this is why. Okay, this is from your supplement. This page, it's called Oxidation Numbers 1. And I didn't go through the rules because the rules are just, you know where rules come from? Rules come from patterns. So we started off with the patterns first. The most important, the rules that really stick with you are the rules that you make up yourself. And so, you know, rather than having you memorize these, you see the pattern and eventually you can write your own rules, right? And so here, the following rules should be applied in the priority order 1 to 5. Underlined elements in the examples were assigned their oxidation numbers first to emphasize this priority. And so we need to go through these because you need these for this test that's coming up. The sum of all oxidation numbers in a species equals the net charge on the species. Thus, each atom in the elementary state has an oxidation number of 0, and each monatomic ion has an oxidation number equal to its charge. And so if we look at elemental mercury, there's no charge on it, and so the charge is 0. N2, each nitrogen. Now this 0 refers to the charge on each nitrogen. And so each nitrogen must be 0. 0 plus 0 gives us a net charge of 0. Each chlorine is 0. So 0 plus 0. Each oxygen is 0. We have 3 of them here. This one, each sodium must be +1, and each sulfur must be -2. That's monatomic. Even diatomics and polyatomic elements, like ozone there, are 0 as well because of the additions. Group 1 and 2 elements are +1 and +2 respectively. Those are fixed charge. So lithium in a compound, lithium alone would be 0. Lithium in a compound is +1. Fluorine is a group, fluorine is always -1 in compounds. And so if this were just F2, it would be 0. But since this is a compound, fluorine gets a -1 because it's not the strongest. There's other patterns to this as well. But here, lithium +1, potassium +1, calcium's +2, sodium's +1, potassium. And then we can figure out the other charge. So if lithium is +1, fluorine must be?
-1.
If fluorine is -1, oxygen must be?
+2.
Is oxygen happy at +2?
No.
No. That means this is going to be an oxidizer or reducer? Oxidizer. If potassium's +1, then phosphorus is? Okay, we have potassium at +1, we have 3 of those. And so the total positive charge will be +3, which has to be balanced by a -3 negative charge. And so these are the charges on the atoms here. And so we have a whole set of rules for determining the charges on the atoms. And so we can go through and figure out the charges. I was just sticking to simple ones. But so group 1 and group 2 go next, and then fluorine's -1. Then hydrogen is +1, and then oxygen is -2, etc. I have a different set of rules that I've written for these, but these are the rules in your supplement here.
Oh, so, okay, so to find the charge, you just have to subtract each ionic charge?
Yeah, so let's do these here. For example, A, determine the oxidation number of each element in the following species. And so what's the name of the first species there?
Chromium.
Okay, so what we do is we do group 1 first. So that means potassium goes first. Potassium is going to have a charge of what?
1.
+1. And then we have 2 of those, so 2 times +1 plus chromium. I don't do chromium yet because chromium is variable charge. We don't know what the charge is going to be. But I should know what oxygen. Oxygen's typical charge is? -2, and we got 4 of those. And so this has to equal 0, the net charge on the compound. And so what is chromium got to be? And so this is -8 plus 2 is -6. That means this has got to be +6. So chromium's got to be +6. B. Oh, well, what does that make chromium? Does that make chromium happy or unhappy?
Unhappy.
Unhappy. Chromium's going to be a good oxidizer. Chromium's going to want to take electrons because it's unhappy. Why we do these is to figure out the redox properties of things that don't appear on the table. Okay, what's next? Lead. What's the oxidation? Well, there's only one atom. It's neutral. Therefore, this has got to be 0. So lead. What are the typical charges of lead? 0, +2, and +4. Those are the charges for lead. C. H3PO4. H3PO4. H goes first at. O goes next at. And we got 4 of those, and then 1 phosphorus. And so phosphorus, I don't know, but this whole thing has to add up to 0. What is phosphorus? +5. So if phosphoric acid were to be something, would it be an oxidizer or would it be a reducer?
Reducer.
It would be an oxidizer.
Oxidizer.
It would be an oxidizer.
So what if there are elements that we don't know the chart, like, because for those examples, we know potassium.
You always have You'll always know the charge of some of them. I've been doing it. When we've been calculating charge, we've been doing it. We can figure them out. Uh-huh.
We could have put -3 if it was different. Like, to get 0, couldn't we put -3 on phosphorus? Like, say the equation was different, to get 0, couldn't we?
Yeah,
Okay.
right, right. Exactly. So for example, like this one, K3P. Potassium is +1. Phosphorus's charges varies from -3 all the way to +5. And so in this case, phosphorus would be -3. That's the only way we could get this equal to 0. And so we're going to see these two compounds behave totally different. Even though both of them contain phosphorus, this one's considered an oxidizer, that one's considered a reducer because it's electron rich. You know, we see this in chemistry all the time.
So reducers are protein.
All the time. So, for example, ethanol. Remember we did ethanol. I don't know if you remember this one, but I wrote out the formula like this, and then I rewrote the formula, C2H6O, and then we figured out the charges. Do you remember doing that?
Yes.
A few days ago. And what are the charges? Which one do we do first of these three? H. H is +1. We have 6 of those. And then we do O at -2. And that means C must be, this whole thing has to equal, in this case it equals 0 because -2. What's the charge range for carbon?
4.
Yeah, 4 to -4. And so what this means is this could go either way, but this could lose electrons or it could gain electrons. Do you see that? And so ethanol can go either way, but it looks like it would rather lose than to gain. Right? And so have you ever heard of wine turning into vinegar? It's true, wine can turn into vinegar under gentle oxidation conditions. In organic chemistry, we would write it like this. We put in a gentle oxidizer. If we put in a gentle oxidizer, then what we can do is we can convert this from ethanol into this. You recognize this one?
Yeah.
This is
Actually, no, I don't know about that.
This is acetic acid or vinegar. In your bodies, this is what happens to ethanol. Ethanol gets oxidized in your body to acetic acid, and then it goes through a metabolic cycle. Eventually, at the end of this cycle, do you know what forms? Eventually what happens is we oxidize because it goes from -2 here to 0 here. Eventually it's going to end up all the way at +4 in CO2. Can it go beyond +4?
No.
No. And so your bodies are going to take the ethanol and metabolize it for all the calories it's got, and then you're going to exhale CO2, which is completely spent. You can't metabolize CO2 any farther, and so we have to exhale it as waste. Uh-huh.
Can we do H and help?
H?
Yeah.
There are 2 ways you can do H. One is, what's the name of H? Ammonium bromide. And so here, bromide should be easy. What's the charge on bromide? Now, this hydrogen is, therefore nitrogen, which is variable charge, must be, hydrogen can be variable charge as well, so you gotta be careful.
-4.
-3. Does ammonium burn? Can you burn ammonium bromide? That's salt. Could you burn sodium chloride? Does sodium chloride burn? No, but you could burn ammonium chloride. It burns quite easily. You could burn sodium chloride under extreme conditions because chloride can lose electrons. When I say burn, you burn it in the oxidizer.
We use K.
10?
K.
K? This one's K. Aluminum, is it fixed charge or variable charge? Aluminum is fixed charge, Dad. Hydrogen is,
1 minus.
and that means oxygen must be -2.
But how would you distribute the 3W over 3H3?
No, we do it per atom. So aluminum, this is the way I visualize it. Aluminum, I did this earlier. This is the way we wrote it a long time ago. This is the way you look at it. There are 3 oxygen atoms. Each of those is -2. There are 3 hydrogens. Each of those is +1, and 1 aluminum at +3. That's the way we do it. Okay, let's take a look. What is the highest common oxidation state of carbon? Highest negative or highest positive?
Negative. No positive.
Well, we know carbon varies from what?
4 to 4.
4 to 4. How did I get that?
On the thing.
From the periodic table. So this is how we got it. Can somebody explain to me how they remembered how they got the charge? The max and min charge? Or the max positive and the max negative charge off the periodic table? Can somebody just explain how to determine the max pos and the max negative charge, maximum positive and maximum negative charge off the periodic table?
You look at
So if we pick carbon, let's just pick carbon. How did you figure out the max pos and the max negative?
Because the last layer is 4 electrons.
I'm sorry?
Because if you count it from like 1, 2, 3, 4, it's the 4th group, and there's 8 of them in total.
Okay.
Yeah.
Anybody
There's
else?
8 groups.
All right, let me tell you, there are lots of ways to remember this. So I just gave like one, but you could think of others. The way I normally remember this is this. The noble gases are very happy, as is, right?
Yeah.
And those can correspond. So if I'm a carbon, that's 6 electrons. Neon has 10. So how can I get from 6 to 10?
You add 4.
You add 4 negative electrons, so that's -4. Or I could go back down to helium. How would I get from 6 to 2? You lose 4 electrons, which gives you a +4 charge. That's how I figure it out. You would do it for all of them. Okay, so does that answer some of the stuff about charge?
Where your element is.
Uh-huh. Aqua regia?
Is the reaction how that absorbs kind of the same how you collect silicon reaction?
That's different. Different. Yeah, gold foil on mercury is different. Liquid mercury, it forms an alloy called a amalgam. That's different, yeah. Yeah. Yeah, that's a different type of reaction. Aqua regia is different.
So bromine is -1 or +1? Because, no, because if you do add 7, subtract 7, that would be the final charge. So add 7 electrons to go to argon. Because the elements will already.
All right.
Wait, so what is the charge of, what is, group 3A? That would be positive 3, 9, and 5?
Yes.
Well, anyway, what you do is with those charges, the max and the min charges, you can figure some stuff out. So, for example, dichromate, is it happy or unhappy? Dichromate. Dichromate, you might think, why does it want electrons? It's got -2 charge. It's because the chromium is,
Plus,
yeah, the chromium is +6. Chromium +6, is it happy or unhappy?
unhappy.
Unhappy. Have you ever heard of that? They made a movie with her story. Gosh, I can't. Her name, though. My memory's bad. It's been a while. She's a lawyer, and it had to do with chromium-6 in water. Did you hear about that? Chromium-6 in water. And there's a book written, and she's appeared on many shows. She's still very active. Erin Brockovich. Have you ever heard of her? She's very famous, but this happened a while back ago. But apparently, this is called chromium-6 or hexavalent, and contaminating drinking water. And a whole bunch of people were suffering cancer. And so Erin Brockovich. There's a movie about her as well. Okay, so those types of charges are important in understanding this, and those are the other pattern. I told you there's some patterns in the redox chart. That's one of them, the pattern of oxidation state for the charge. So again, we're all over the place, but basically it's metathesis. Can you do the conventional, the driving force? Can you do the driving force?
Yes.
Can you do the conventional equation, the net ionic and the ionic?
Yes.
Can you do the AB plus CD pattern? Then you're good. Okay, what's next? Acid base.
Yeah.
Can you use that acid base chart? Can you inventory?
Yeah.
Yeah, go back and look at the example we did. If you can do that example on your own, then you're good. A lot of people can't do that example we did on their own. Can you do redox? Well, what are the redox? List all the redox reactions we did. Combination, element plus element combination. What was the next one? Single replacement was the next one. But single replacement had some issues. Well, what were the problems with single replacement? Can you list? Not everything works because of oxidizing acids. Because of what? Because we're trying to fix a role. A is supposed to play this role, but what if A does not want to play that role? B is supposed to play this role. What is the role of A? What is the role of B? What if they don't want to play those respective roles? And so that's the failure of single replacement. All of the exceptions boil down to A and B not playing their roles as assigned. You're some director of a play or movie or whatever, and the actors don't want to play the roles. What do? You can't force them, because the actors in this case are chemicals, and nature's going to just take its way. And so all the exceptions they're exactly the same reason. All the exceptions are because we're artificially placing A into this role and B into this role. That's artificial. All the exceptions are the same, even though I listed specifics. That's something you get after you look at the data. And then what can we do? You either memorize the exceptions, so what doesn't play its role? Oxidizing acids don't play the role. What else? Halogens like chlorine, bromine, iodine don't play their role. What else? The solvent water. Water is supposed to be a spectator. It's supposed to be a solvent. It didn't play its role. Right? Those were the 3 exceptions I talked about in class. Do you remember those or not? Okay, and then well, you don't even have to remember it, because if you use this technique, then you don't have to worry about it. What technique was that? It's a very simple method, step by step. The chart method. If you do the chart method, then you don't have to worry about A and B not playing its role, because you aren't assigning the roles before the actors. You're looking at who the actors are, and then based on who the actors are, then you're assigning the roles, right? The single replacement has it flipped. And then we're done. That was it, right? Except for combustion. Combustion of those is very simple. Oxygen yields CO2 and water. So all we did was metathesis, and we spent nearly all our time in metathesis, AB plus CD, and then we did acid-base, Bronsted, and then we did redox, element plus element, single replacement, and chart. That was it. That's much easier than all the patterns. Where's the memorization sheet here? In the supplement. It's much easier than memorizing all the patterns in the supplement. Well, in my opinion, it's much easier. It depends. Some people much prefer memorizing. Okay, but there's a pattern of things, reaction types to memorize. Not in mine, but probably in your supplement, because my supplement's old, I think, looking at it. Okay, so those are the reactions. Those are what you should know for the test. Now, once you get into it in a little bit more detail, then we can go, we can figure certain things out. So, for example, this. Let me tell you about sodium nitrate. Sodium nitrate, what are the chemical properties of sodium nitrate? Metathesis, no reaction. All sodium salts are soluble, all nitrate salts are soluble. Acid base, no, sodium is neutral. Nitrate is so weak we don't even consider it a base. Redox. Nitrate is sodium is an oxidizer. Is it a very decent oxidizer? No, nitrate is a decent oxidizer. So sodium nitrate is an oxidizer. That's what we call it. How about something like this? This is a bad combination. This is like ammonia and bleach. What makes this like ammonia and bleach? Because I have my ammonia, or ammonia-like, NH3 is -3 plus 1. Ammonium is -3 plus 1. So when I look at ammonium and ammonia, acid-base, they're opposite. Ammonium is an acid, ammonia is a base. So acid-base, they're opposite. Redox, they're exactly the same. And so in terms of redox, both of these are combustible. Both of these are susceptible to being oxidized. But the bad thing about this is this. What is nitrate? Nitrate is and so ammonia is a reducer. Ammonium is a reducer. Nitrate is so we have an oxidizer and a reducer in the same compound. If we look at this one, sodium is an oxidizer, but how good of an oxidizer is sodium?
Not well.
Sodium is at the bottom of the list. It's one of the worst oxidizers there is, so we don't even worry about it. Do you worry about consuming sodium ion? No. It might increase your blood pressure, but I wouldn't worry about it oxidizing anything. Versus, would you worry about consuming silver ions?
Yes.
Yes, you worry about that. And so ammonium nitrate is a dangerous mixture, but the thing is, it's in the same compound. And let me show you this. Have you heard of Texas City? was trying to start chapter 10, but there's not enough time to start it. We'll look at Texas City instead. Didn't get the right video though. What happened at Texas City was the worst natural disaster, and there are a lot of Texas City videos that.
Oh, 70 years ago? That's ancient.
Yeah.
Just want to make sure I have everything. Chapter 5, 3, and homework, exercise A, exercise C, and lab 3 and 6.
No. The exercises you can do later. The exercise A, you know, since I missed that particular lab, you'll want it done. Exercise A for sure. The nomenclature. Well, actually, I should collect that, shouldn't I? Yeah. Except the other ones with the chemical reactions, those you don't have to do. Just do the homework one.
Is that exercise C?
Exercise C, right. Exercise C is the net ionics, right? Net ionics.
It was the one that was attached to the lab that we did last time.
Yeah, that one you don't have to have. Let's see, is this it?
Texas City is trying to outlive its past. This is Charles Hancock. Texas City is trying to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around. And today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives. The explosion of the French freighter Grand Camp left an entire town dazed and confused.
And I ran as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
And when the lights just went out, I could not see more than 2 or 3 feet. I thought, my God, it was a nitrate explosion. I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Past a car, which 2 people have been decapitated. When I passed one of the 2 little planes that were flying around overhead, came down along the path that I took up to the town.
I'm sure all of that glass came into us, and I must have gone like this, and so my arm was all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it, and therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it moved me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, and it jarred, but nothing hit me.
Here comes another explosion. But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
We had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a little while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
Sorry, this was actually part 2. This is part 1 to it, but there's no time. So ammonium nitrate is a dangerous chemical because